So depending on how we define importance or influence, the result changes. So that's why we have different measures of centralities for networks. So, and there are different people who would be the most influential person depending on that measurement. So we have the concept of degree centrality that matches with Junda's answer, that the person with the highest immediate contacts, the highest degree, would be the most central. So in social networks, this is considered as influence or power in terms of prestige, and the social role that that is played by the person with the highest degree is like the center of a hub. For calculating degree centrality, we just calculate degrees. Just degrees of nodes would be a measure of centrality. That is called degree centrality. Another idea is closeness centrality. This is about reaching other people. So, for example, if we have a social network and we want to see who is the most influential person to recommend a product, maybe for that purpose, closeness centrality is more relevant. That's why many companies would pick celebrities because they have high closeness centrality. Many people follow them. That's why the distance between each person in the in the market and that so-called influential person is they are close. So it's about reach. And in this sense, the social influence or social power is represented in terms of fastest access to other nodes and how the information flows in the network. Because if that if that company has limited budget for using word of mouth advertising, and they just go to a random person in that social network, and that person is convinced or that person is willing to advertise and promote that product, the reach from the message of that person, which is information flowing in the network, would be limited to their friends, to their immediate contact. But in case of let's say a celebrity on social media, their message reaches to all their followers, for example. So in that sense, the most influential person for reachability can be found using closeness centrality. So in this sense, the social role that the node plays would be the role of a transmitter of information. And for calculating closeness centrality, we can use the concept of distance. So we calculate the shortest path, or so-called geodesic distance, and then we add all the geodesic distances for one node to all the other nodes, and then invert that. Because when the distance is smaller, closeness is higher, right? So that's the concept of closeness centrality. Then another very interesting concept is betweenness centrality. So this comes from the work of a sociologist who came up with the idea that also being in between two different parts of the network gives some unique influence or unique social power. In this sense, power is defined as control or mediation. So the social role that the node with higher betweenness centrality plays would be the role of a broker, a gatekeeper of information, a bridge or a liaison. So, and for calculating betweenness centrality, we iterate over every pair of nodes and check how many times the node of interest is on the shortest path between two other nodes. So if a node is typically on the shortest path between two other nodes, this means that for information, they are pretty much they could be the gatekeeper of information, meaning that if they decide not to communicate a message, they can impact the flow of information in the whole network. So this is the concept of betweenness centrality, and using pretty much the definition, we can have an algorithm for calculating it. And then another concept is so-called eigenvector centrality. This is about being close to other people of high influence. So in this sense, we define centrality or power as the influence of one node. It depends on the influence of their neighbors, plus the influence of neighbors, but with a kind of a lower weight, plus influence of neighbors of neighbors of neighbors, right? Neighbors of distance 3 with further reduced weight, and so on. And we can take this mathematical equation to infinity, then there would be a connection to eigenvalues and eigenvectors. So this is the same concept that was used maybe 20 years ago by Google, by Larry Page, who was one of the founders of Google, and that led to success. I mean, one of the success stories of Google was that as a search engine, it could give you relevant results. So it could rank it was like a pretty much information retrieval. So other search engines could not rank the results as well as Google. That's one advantage that Google had at that time. And the reason One reason was that they were using the so-called PageRank or eigenvector centrality to find, to find the most influential result based on how different websites link to each other. So in this sense, power is based on access, and the social role is like lobbyist, because based on this definition, power or influence is about who you know, right? So if you know the president, if you know someone important, you could play the role of a lobbyist. All right, so back to the network we had. This is the same network. This is called the kite graph. So the answers that you gave about who is most influential, all of them were correct. For example, someone said Diane is the most influential, so Diane was node A. Diane, according to degree centrality, is the most important person. Also, based on eigenvector centrality, Diane or node A would be the most influential person in this network. Then we have node D, which was Heather. Heather had the highest betweenness centrality. And one of you, Harry, right? Harry mentioned that Heather would be the most influential person. And then based on closeness centrality, actually nodes B and C have the highest closeness centrality because they are closest to all nodes of the graph, meaning that they are directly connected to 5 other nodes. So each of them has a degree of 5, but also they have path length of 2 to 3 more nodes and path length of 3 to 1 more node, which is here. So in terms of closeness centrality, B and C are the most central nodes. All right, so let's now see this in Python. This is here I'm loading NetworkX library. So NetworkX library is very useful for working with graphs and network data in general. So here we want to create a network that looks like this. So it has 5 nodes, 1 all the way to 5, and these are the degree connectivity patterns. 1 is connected to 2, 3, 4, and 5. 2 is connected to 1 and 3, and so on. So we can create that graph using nx.graph. That would be an empty graph. Then we add edges. We add nodes and edges. We add the 5 nodes like this, and all the edges by just as pairs of nodes. Now, now we have this graph as a graph object, and we have called it G. Now, if we use this command g.number of nodes, it confirms that it has 5 nodes, and g.number of edges, it gives us number of edges, which was 6. So we had 6 edges. We can also list the nodes. It gives us the list of nodes and list of edges. As you can see, we get this very much similar to how we added the nodes and edges. For removing nodes, we can just use .remove node. When we remove a node, all the edges that are linked to it will be removed as well. For removing edges, again, very similar. We can also add attributes to nodes and edges. For example, adding a node and having a node attribute like occupation equal to student. It is as if this is a social network. Node number 1 is 1 person, and we want to also save this information about this attribute of the node on the graph object. We can also have weighted edges like this. Here we're adding a weight of we're adding the edge 1, 2 with a weight of 5. We can also create weighted edges using this shortcut. If you provide a list where in each list we have like 3 tuples like this. The first one would be the first node, second node, and weight of that edge. We can also create directed graphs if we use nx.digraph. That gives us an empty directed graph. And then using the same method as before, we can add nodes and edges, but the result will be slightly different. Can someone tell me what would be the difference between this chunk of code and this? So I can copy it if you want. What is the difference? Exactly. So for the first one, we get a so-called undirected graph, which means that the edges are reciprocated, same as saying the edges are bidirectional. For the second graph, we get directed edges that have a source and target. So for the second one, the first edge is an edge from 1 to 2. Then we have this edge from 2 to 1, right? These are 2 different directed edges. But here, we're providing this, but when we use 1 to 2, the undirected edge 1, 2 is created, and this doesn't really make any impact. All right, now for this directed graph that we call DIG, number of nodes is I didn't run this. Number of nodes is 5, and number of edges is not 6 anymore, it's 7. This is because here we are providing a list of 7 tuples. Those 7 tuples, in case of an undirected graph, would create 6 edges. In case of a directed graph, the same 7 tuples give us 7 edges. All right, another shortcut that allows us to convert directed graphs to the corresponding undirected graph and vice versa is, as you can see, if we have graph G and we want to convert it to the corresponding graph whose edges are just like G but they are directed, we can use this. And if we have directed graph graph called DIG, and we want to convert it to the corresponding undirected graph that doesn't have directions on the edges, we use the second command. All right, now back to the example of centrality. This is the kite graph. We can load this kite graph. This is a very well-known example. We have it already in the NetworkX library. And we can draw the kite graph that we just loaded. It looks like this. This is the same graph as this and the same as what we had on the slides. All right, so last time that we were talking about network science, I told you that we have different levels of analysis. We have node level of analysis, dyad level, cluster level, and network level. So with node level, for example, this idea of calculating centrality measures and checking, who is the most influential node or what is the most influential node is a node level analysis because we're comparing nodes essentially. So for degree centrality, we have it already in NetworkX. So for that graph, these are the values of degree centrality. I have sorted them, and node 3 has the highest degree centrality. So we can see that node 3, which is in here, is Diane from the example. So this is same as Diane in here. And Diane has the highest degree centrality. This is degree centrality where we also divide by the maximum degree. Therefore, the values are all between 0 and 1. There were a total of 10 nodes, right? Therefore, the highest degree that a node can have is 9. When you have 10 nodes, each node can be connected at most to 9 other nodes. So the highest degree is 9. Therefore, for node number 9 that has a degree of 1, 1 is divided by 9, which gives us this value. Node 9 is here. It has a degree of 1. Instead of representing this as 1, we represent it as 0.111, repeating. All right. Betweenness centrality, again, we have a function for it in NetworkX. Here, again, I'm sorting them. And for betweenness centrality, we can see that node 7 has the highest betweenness centrality, 0.38. What this means is that header in our network, header is on the shortest path of any other pairs of node 38% of times. So whenever you consider 2 random people from the network, and what is the shortest path between them? What is the easiest way that a rumor goes from person A to person B in that network? 38% of time, Diane has the unique ability to stop that rumor or boost it, right? So this is about information flow. So Diane was the highest node in terms of the most influential node in terms of betweenness centrality. Then closeness centrality, again, we have a function for it. Nodes 6 and 5 have the highest closeness centrality. 6 and 5, these are the nodes that can reach, each of them can reach 5 other nodes directly. For example, node 6 is a friend of 7, 5, 3, 1, and 4. So, I mean, it knows more than half of the other people in the network directly. So it has many connections, right? But then, also these immediate neighbors give node 6 some social power because they can introduce node 6 to their friends. So node 6 can reach 3 other nodes by just asking one of their friend to introduce them. So node 6 can reach node 8, 0, and 2 using 2 hops. So for example, for node 6 reaching 2, this is the shortest path. Node 6 reaching 0, this is the shortest path. And node 6 reaching 8, this is the shortest path. And the node, and only for node 9, they have a path of length 3. So this means that with 3 hops, they can reach any other node. So you might have heard of 6 degrees of separation. Have you heard of it? So there was a study a few, I guess maybe 2 decades ago, or maybe even earlier. All right, so 2 studies. The initial study was just about sending letters to someone you know. All right, starting from west coast of US, they were trying to reach a specific person in New York. And this was like an experiment. They started by sending a letter to someone they knew who was closest to New York, right? And then in the letter, there was instruction saying, send this to someone you know who could be closest to New York. To eventually, we want to find this person, some random person in New York. And then only after a limited number of mails, they actually reached that very random person. So maybe that number was 7 or 8 or something, right? Then later, there was another study. Actually, the first study, the average length was 6 point something. And then there was another study that showed any two people in the US could be connected through a shortest path of length 6. And by any two, it meant that you could reach the president of US with 6 hops on average. Any person in the US, they know someone who knows 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 the president. It was 6. I mean, I studied in New Zealand. There was a telecommunication company called 2 Degrees. And it was based on this idea that in New Zealand, everyone knows everyone with an average length of 2. Because the country is smaller, it has 6 million, population of 6 million, and people know each other also, like culturally they are close-knit. The average path length in New Zealand was 2 degrees of separation, meaning that any other person in New Zealand, you either know them directly or indirectly through one common friend, right? This is average. Of course, there could be cases deviating from the average. And now, I mean, more recently, the global degree of separation could be around 6 or so. If we assume that, let me just write here. I think I remember the formula. It was something like this. This is how we can kind of estimate the degree of separation. If we assume that on average, every person in the world knows 50 other people, then the degree of separation in the world would be log of population of the world, which is what? Is it 8 billion already? All right, 8 billion divided by log of 50. This gives you the degree of separation of the world based on the assumption that the average person knows 50 other people. So you can calculate this using a engineering calculator and see what number you get. Maybe it's 8 or something. But actually, with the advent of internet and social media, I think the average number of people that each person knows is much, much higher than 50, right? I mean, it depends how you define knowing someone, right? I guess like each of us have hundreds or thousands of LinkedIn connections, but we don't really know them, right? But let's say, we kind of scientifically define what knowing means, and then I would say the average number of people that every person knows is more than 50, at least based on how I think about the board. And what that means is that the degree of separation in the board is even smaller than this value, meaning that we can, on average, reach any other person anywhere in the world by a limited number of hops, maybe 7 or 8 or something, or maybe 6. And I'm talking about everyone. So just randomly pick some country, randomly pick some, I don't know, some coordinates in the world. There is someone living there. The average distance we have from that person is limited. It's not 100. It's maybe some one-digit number, but on average. All right. So this was, and then eigenvector centrality, that's similar to the concept of PageRank. So PageRank is same as eigenvector centrality, but for directed network, because the network of links between different web pages is a directed network. So based on eigenvector centrality, node 3 has the highest eigenvector centrality. That was Diane from the example. All right, so this is the network of Florentine families. You may remember it from previous lectures. These are the nodes. Each node is an Italian family from 15th century in Florence. This is the representation, the visualization of the network. So these visualizations used to be very popular, like 10, 15 years ago. But now, some people call them ridiculogram, meaning that it's ridiculous to represent a network like this, because this doesn't really show what is going on. But many people really like these visualizations. All right, so who are the top 3 families in terms of degree centrality, betweenness, closeness, and eigenvector? We can see, okay, this is just an exercise that you can work on. And here is a matrix representing the social interpretation for every combination of high and low centrality for 2 of these measures. For example, low degree and high closeness means this in the social sense. low degree and high betweenness means that they can, they can be the gatekeeper, a port of information exchange, and so on. All right, so then at the higher level of analysis, we have dyad level. That's when we look at the edges. For example, in graph G2, which was this Florentine families, we have 20 edges, and we have these nodes. So if you want to check whether family Medici and family Peruzzi were connected by marriage, so each edge was a marriage, if you want to check that, it shows 0, meaning that there's no edge between them. As there's no edge between them, now we want to know what is the length of path between them. So there is a path between them, meaning that they are not disconnected. These are all the paths between these two families, meaning that if Medici family, which was the powerful family, if they wanted some other families to mediate something between them and the Peruzzi family, they could just ask Barbadori to ask Castellani to kind of mediate a conflict. And so, but for finding the shortest path, this is actually the shortest path. So this was the kind of easiest way of finding a mediation. And I mean, both because of betweenness and closeness, which is about shortest path, Medici family was the most influential family in Italy at that time, so much so that they are still among the most important families in Italy. But interestingly, this power is not because they were like wealthiest, right?